Check, 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 check. All right, let's do this, guys. Oh my gosh. Okay, all right. Oh my gosh. All right, guys. Well, welcome back to Better Biomed. I know it's been a few days. It's definitely been some days. I have been so incredibly busy. Not only did I do a bit of traveling there for a bit, but, you know, I've also moved back into the studio, and I've been setting everything up, and it's an incredible endeavor to do. So, guys, today we're covering fundamentals of electricity and electronics, which should be kind of an easy one because that looks so cool, by the way. I do a lot of work with electronics, so I don't think it's going to be that tough to go into. However, with this particular topic, there are formulas. And with formulas, you're going to want one of these and probably one of these. So, let's just take that page off. And now we got a clean slate. Let's do it. All right, so got this guy over here. I got my flashcards, and I got the fundamentals sheet. Now, before I was going over lecture, and then the next day I was doing flashcards. However, this one here is not that scary. It's only a couple pages long, which is kind of crazy. I would think it would be more, but that's okay. We're gonna get through it. We're gonna do some flashcards, which, Jesus, is this all for the same? It is. Okay, so it is. So, folks, we're going to get into it. I only have a couple days left. 1 day left until I take my CBET exam. So we are going to do this. And Wednesday, I'm taking my CBET. So, I'm going to cram as much as possible. So today we're going to go into this, and then probably there's a good chance that tomorrow throughout the day, I'm going to be doing other like sectioned off live streams. And that's just because I'm going to cram as much as I can until tomorrow night. And then the next day I take my exam. And then I'm probably going to do a follow-up video after the exam. And that's because whatever I didn't like about the exam or something, we're going to go over that. We're going to definitely hit it up. And I'm going to see where I failed in my studying and where I was just completely wrong. So, with that being said, we're going to get this party started with the foundations of electronics. All right. I see, I got to have a place for that, someplace. Okay, you got your pencil and everything ready. We're going to do some formulas. Let's go ahead and kick this bad boy into the split room so you guys can see what I'm doing. Let's go ahead and shine some light on the situation. All right, I take it that that's reasonably passable. Oh my God, guys, my shop is an absolute mess. I know you can't tell because of this here, but trust me, I've got slot machines and stuff like that we're going to be doing some videos on. I'm right back here, right behind me, and we're going to be tearing into that stuff as soon as I'm done with the test. Okay? All right. Fundamentals of electricity and electronics. Foundations of electronics. Electricity. Electricity has three primary parameters: voltage, current, and resistance. Electronic voltage is the difference of potential between 2 points in an electric difference of potential energy between 2 points per unit electric charge. Ugh, I hate that, the way that that's worded. That's horrible. It's a difference of electrical potential between 2 points. That's pretty much it. That is it. And so, and believe it or not, you can have difference of potential between 2 points on a ground wire. It's true. All conductors can carry and induct current. That includes simple things. All conductors. So ground wires too. So electricity has 3 parameters. It's measured in volts, which are equal to a joule of energy per coulomb of charge. I really hope that's not on the test. Electric current. The flow of electric charge is measured in amperes or amps, which are equal to the flow of 1 coulomb per charge per second. And electrical resistance is the measure of how difficult it is to pass an electrical current through a conductor. It's measured in ohms, which are equal to volt per ampere. Well, that's interesting, I guess. It's kind of true. But according to all the experts more recently, current is not through a conductor. It's actually an electrical magnetic waves going in and out of the conductor down the field. So, these are just generic terms. I get it, but there's plenty of videos that explain how electrical current really runs. It's not like it's pushing electrons down through a wire like the garden hose analogy that everybody's used to. That's not it at all. In fact, it's in waves, electromagnetic waves, through electromagnetic fields, really, down through the conductor. So that's interesting. Okay. So the relationship amongst these 3 quantities is known as Ohm's law. It states that the current is directly proportional to voltage and is given by the following equation. So this is the absolute fundamentals of everything that we do. V equals I times R, all right? And because of so normally I think it's done like this. All right, there you guys can see it. And likewise, whenever you can do multiplication, you can also divide. So, using these principles, there's one thing that you guys got to take out of this. Sorry guys, I only got like 2 hours of sleep last night. So if I appear like I'm lingering on and whatever, now you know, okay? So V equals IR. So let's take some pretty typical measurements. How about an electrical device right behind me? So we know that our electricity here is about 120 volts. 120 volts. And it's equal to I times R. So it's a constant if the I and the R are constant. Well, behind me is an electrical device, and it says that it has a 1200 watt heating element, which we'll get into in a little bit. But that's like a what, 11 or 12? Where's my calculator? Sorry guys, hold on just 1 second. Every single time I do this, I have to select my second menu or my second monitor because it always wants to change that up. Okay, let's do... So one of the cool things is you can come in here and do an Ohm's law calculator. And I love the fact that they have this little graphical representation. So even though I write all these fancy formulas down, you can see them here quite plainly. But if you want to do some quick calculations, you can pull this out on your phone. So we know that we have 110, let's just give them the benefit of the doubt, 120 volts. And we don't know the current, okay? But I do know that my element, my heating element, is listed as 1200 watts. So once you have 2 of the 3, you can figure out the third parameter. Calculate. So here we go. Since I know the power and I know the voltage, I know that I have a 12 ohm heating element. So when you guys are thinking, when am I ever going to use these formulas? I use these formulas all the time, especially when I have a device back here behind me that is popping fuses, and furthermore, it just automatically appears to be running irregularly. So I pop my electrical safety analyzer on current and I measure the current. Well, here you can see the current should be about 10 amps. Now, if you guys are aware, on standard AC electrical systems, you have 15 amps as standard. And if you're in a commercial or industrial facility, you probably have 20 amps per circuit. Most modern day homes also have 20 amps on many circuits. So I'm safe, right? It says here that my heating element, if it's 1200 ohms or 1200 watts, that I should be seeing 10 amps. So when I pop it over on my electrical safety meter and I put it on current and I'm sitting there and I'm staring at it and I'm getting 15 to 16.5 amps. Whew, what's going on? So this particular device that's right back here behind me, it starts out low. It starts out like 10, 11 amps, and then it goes all the way up to 15 or 16. Well, if the voltage stays the same, which it should be, unless you have some voltage sag, then the only other thing that's changing is your resistance, which means the heating element is actually dropping resistance in order to increase the current. Because as you decrease resistance, the current is inversely proportional. So let's go ahead and let's plug that in. I am seeing 16.5 and 16.6 amps and worse. I unplugged it before something caught fire, but it was getting worse. So let's see what our watts are, and let's see what our resistance is, because the only thing that's changing probably is the resistance. Oh my gosh, here we go. All right, take a look up here. We have 1980 watts. Now, it says on the data plate of the device 1200 watts. Now, a lot of electrical safety meters aren't going to measure watts. All right, they will tell you amps, but thanks to this fantastic Ohm's law, it doesn't take very much to figure it out. And you can always go to calculator.net or some other place like this from your phone, pull it up and take a look. What do you see? And you can do these measurements in the field. It's really quick. You don't even have to do the math. Hell, I don't even do the math. I let these calculators do the math because I'm usually doing multiple things at once. But I do want to check the math. So if you look at here, it says that my heating element, which is supposed to be what, 12, 13 ohms, it's almost halving, which means it's down at 7 ohms, 7.27 according to this. And that's when I disconnected it. So what's it doing? It's actually working its way towards a dead short. Extremely dangerous, because if you get to a dead short, it's a stainless steel body. That means when it does go to a short, the heating element, the internal element to the external element, it's getting to be a dead short. And when that happens, you're going to have a massive amount of electrical leakage. So this is why it's extremely beneficial for you guys to know the math, or to at least understand where you can calculate the math, so that if you encounter something that's really weird, you can solve it using your own brain, okay? I had another item, very interesting item. It was a thawing unit. So it was a Helmer thawing unit, and it's got agitators that move up and down into a warm water bath. And it just agitates it so that you can thaw your blood and stuff rather quickly. Well, that item there, it was popping. I think I had 9 or 10 amp fuses. It's not really a fuse. It's a resettable fuse slash panel mounted circuit breaker. And hold on, I'll show you what that kind of looks like. I think I did a video on it. After a while, like we just forget what we did videos on, what we didn't. All right, so they want to do equipment circuit breaker, through wall. It should be a through panel. Okay. Let's see, what would they call that? Okay, there we can see an example one up here in the corner. You see this guy? That is a through panel circuit breaker or resettable fuse, depending on, you know, what you want to call it. They call it here a push button reset circuit breaker, yada, yada, yada. Anyway, this item here was on a Helmer blood warmer, and it had a capacity of 10 amps. Well, it was popping. And you're like, wow, should it be popping? I don't know. Well, first thing, you discovered that it is popping. Next, you have to measure, right? We measure things. So I got the electrical safety meter, put it on amps, and I measured it, and I had to stick my phone recording the screen of the electrical safety meter because it would just randomly pop. It would be sometimes 30 seconds, sometimes 4 or 5 minutes. So I just set my phone to record, and I sat back and I just let it warm up and do its thing. Well, it was popping, but it was popping at 8.5 amps. So the capacity is 10, it was popping at 8.5 on a spike, according to the video. So that tells you right there that these resettable breakers can and do go bad. I proved it because of the math. Also, you can do the math based on the data plate. Always check the data plate on your equipment, because they should tell either the amperage of the device. If it's got a heating element, it'll tell you the amount of watts. If it tells you either of those, you can do the math, Ohm's law, figure it out. And if you don't know Ohm's law, you can come in here and you can do a calculator. And I just gave you 2 examples right there, 2 scenarios where you had to know Ohm's law. Other words, you're just chasing your tail. You're like, oh my gosh, it's tripping. When breakers trip, people do things like replace motors or replace heating elements. Well, did you measure it? You can measure a heating element while it's cold and while it's hot. You can measure current, motors. You can measure it, you know, the coils. You can measure the current that a motor's pulling. I mean, there's many ways of doing it. You don't just guess. So many biomeds out there guess. So that's why this is such a vital piece of the test. All right, so here we go. I know that seemed like it was a little long-winded, but trust me, guys, this is actually extremely important just because of the nature. This is the difference between a junior technician and a senior tech, as they actually know what the heck they're talking about. Okay, so electrical power. Electrical power is the rate of doing work. It's defined as P equals I times V. So that's power equals current times voltage. So using that math, power, let's use my example back here, the 1200 watts equals current times V, volts. Well, just based on this, my current for 1200 watts should be, what, 10, 11 amps? Let's just figure out, let's do the math. Let's do 10 amps, volts, excuse me, 120 volts. So 10 amps times 120, I don't even need math. There we go, 1200. That's what we should be seeing. Oh, there we go. That's what we should be seeing, 10 amps, 120 volts. So the math does jive, okay? So, They do have little business cards, I believe, that have Ohm's Law and the different variants of it. I'll see if I can dig some of those up, and maybe I'll hand them out to people, along with maybe some Better Biomed stickers or something. Absolutely essential. All right. So over here, it says P is electric power, I is current, V is voltage. Power is measured in watts, which are equal to a joule of energy per second. That's a way to confuse somebody. Multiplying power by time results in total energy, usually given in kilowatt hours. Now, where have you heard that before? Kilowatt hours. Well, hopefully, if you're paying an electric bill, you're studying what items in your electric bill use a certain quantity of kilowatt hours. Now, I did a whole video on the kilowatt, which is a device you can plug in and you plug other things into it, and you can measure every individual device and how much current it pulls, measured in watts, kilowatt hours. You are charged by the electric company based on the quantity of kilowatt hours that you use. Okay? It says here, for example, if a light bulb draws 500 milliamps from a 120 volt source for 8 hours, the energy is used can be calculated this way. Well, you know something? I know that they're going to do the math here, but that's not realistic math. The realistic math is bulbs are rated in watts. So let's do a 100 watt bulb, and we're going to do the, let's see, what are we going to try and figure out? How about the amount of current? So we got a 100 watt bulb times, we know the resistance, we know the current. Okay, so let's do, so that would be 100. Is it I squared R? Here's where I'm going to fail. 120 volts, which I'm pretty sure it's 110 volts. We got 100 watts. Tell you what, screw it. Let's cheat. Let's absolutely cheat, because I don't even care. We got 120, and remember we have the 60 watts, or no, 100 watts. Let's figure out how much current we're pulling. Calculate. We're pulling 0.83 amps constantly. So how many light bulbs can you have on a 15 amp circuit? If every single light bulb's pulling 0.83, but that's for a 100 watt bulb. Now let's see if we do a 60 watt, which is more typical. We're doing 0.5 of an amp. A little more realistic. But let's do a modern LED bulb at, I don't know, what, 7 watts? 9 watts? Let's do 9 watts. I think it's pretty typical. Okay. So 120, 9 watts, we're pulling 0.075 amps. That's right, guys. So down here you see the math. It's we got the watts. I equals P over V. So we've got power over voltage. So that would be our 100 watt over that equals current. Yeah. All right. I should have known that. Okay. So this is current. LED bulbs, as you can see, they use, LED bulbs use a considerable amount less of current, 0.075. So let's go back to it. 60 watt is a typical incandescent bulb. That's half an amp constant. That's already like what, 10 times the amount of electricity as an LED bulb. And let's step it up even more. External bulbs, floodlights and stuff are very typically 100 watts. It's almost 1 amp. So you're going from 0.07 to 0.83 amps. It's a big difference in the amount of electricity you're using. So anyway, there we go. Ohm's law, electric power. Fantastic. Let's get back to this. My brain is definitely a little discombobulated, guys. That's what happens when you only get 2.5 hours of sleep. Okay, find the equivalent resistance in the circuit. Well, we've got voltage and we have the resistors in series. And when you have the resistors in series, you've got 6 ohm, 8 ohm, and 12. They're added together. So it's basically 12 ohm plus 8 ohm plus 6 ohm. So we can figure out the resistance right away. I mean, if it wanted the amperage, that would be the next thing that we'd have to figure out. But 12 plus 8 plus 6, so we've got what, 14 plus 12, that's 26. I believe, right? 12 plus 8, yeah, it's 26, yeah. I'm second guessing myself, guys. Okay, it says here, oh, well, shit. They give the answer. Go figure. And when resistors are in a simple circuit arranged in series, their equivalent resistance is the sum of all their values, 26 ohms. Okay, so resistors, when they're in series, you add them up. When they're in parallel, that is when we do some math. So, you know, electricity takes the path of least resistance. So it's the reciprocal of all the sum of the reciprocals of the resistors. It's not as bad as you guys think it is. Okay, so here what they're showing is you got 4 ohms, 8 ohms, and 5 ohm. So you take the 1 over, so let's say 4, so you got 1 over 4, and then you're going to do the next value is 8 ohms, so 8. And then the next one is 5 ohms, so 1/4 plus 1/8 plus 1/5, and then you're going to do that over 1. So, and then it's going to come out to 1.74. Let's check the math and see if it jives. Okay, let's see, 1 divided by, and then we're just going to do the parentheses. 1 divided by 4 plus 1 divided by 8 plus 1 divided by 5th. Boop. And we're going to close the parentheses. Oh, gosh darn it. And of course I'm getting a phone call. So here you go. 1 over 1 divided by 4, 1 divided by 8, 1 divided by 5 equals 1.739, so 1.74. Not that bad, right? I guess it really does make a lot of sense when you see it like that. So the reason that I've had to know these two things specifically is because when you're making jigs, jigs specifically for things like, let's say, ESUs, and they need 13 ohms to calibrate the REM circuit. Are you going to have a 13 ohm resistor? You might. However, if you do a parallel series hybrid configuration, you can actually get there by grouping resistors together, and then you can put them in parallel or in series to add them up. So let's say I need 13 ohms, I can group a series of them together and I get 5 ohms, and then I can group a series of them together and I can get, let's say 10 ohms. You put them in series along one another, and what you end up with is 15 ohms, or pretty darn close to it. So I have had to do a parallel series configuration on several of my jigs in order to get the resistance exactly where they want it, or also depending on the wattage of the resistors. Okay, and I don't know if they're going to talk about that, probably not, but you do have 1/4 watt, you got like 1/8 watt, you got 1 watt resistors, 5 watt resistors. And the wattage is basically the amount of heat that the resistor can handle. So if you're going to do things like energy dispersion, then what you're going to need is you're going to need a very heavy wattage. And the only way to do that is usually to put resistors in series. because by putting them in series, you're balancing out the electrical current amongst multiple resistors instead of running it through one. So if you have a parallel series configuration, but one of them that is in series is a 1/4 watt resistor, then the functional capabilities of your entire circuit is 1/4 watt. That's it. But let's say you take 2 resistors and you put them in parallel. Let's say 2 5 ohm resistors or 2 10 ohm resistors. You put them in parallel, and now you've got 5 ohms essentially, I believe. Or no, 2.5. So you've doubled the amount of wattage that it can handle, the amount of heat, but meanwhile you're decreasing the resistance, because when you put them in parallel, what you are doing is you have to do the inverse or the reciprocal of the sum of the reciprocals. That's so frustrating. This is one of those things where I have written on that business card I mentioned earlier, so you don't have to figure it out when you're in the field. You can just run the math really quick, and there are calculators that do this for you. In fact, let's do that. Let's come over here and look at this. We have resistors calculators, but look down here. Notice how it has parallel resistor calculator. So let's see, my example I gave earlier is 10 and 10. Oh, I gotta separate them by a comma, my bad. Okay, there it is. So you add 2 values together. If they're in parallel, you're half the value. And if you put them in series, so let's do the same thing, 10, comma 10, we're gonna get 20. Here it is up here. It moved around on me. Okay, so when they're in series, you add them together, and when they're in parallel, if there's 2 similar values, it's half the value, okay? Because you're splitting the current amongst 2 different pathways. Okay, let's get to it. Who's in here? Romeo, Roy Ryan, what? I have not made any announcements for the study group, guys. This study group is basically for me, and I'm allowing you guys to be part of it. Be part of the magic, I guess. All right, let's get back into it. All right, so that is resistors. Now, funny thing is when you're doing capacitors, it's the exact opposites. And let's see, are they going to get to that? Let's place this guy over here. All right. Oh, no, we're doing voltage drops. Okay. Hold on. Let's see, that was page 35, 36, 37. Okay, we're not going to go into capacitance yet. We're going to start doing voltage drops. Okay, find the voltage drop across the 1K resistor. Voltage division is a tool that allows the calculation of voltage across resistors in series. It uses this equation, which is VI equals voltage of the source. I don't know if my camera's picking that up. Times Ri over R1 plus R2 plus whatever. Not fun, man. Okay. VI is the voltage across the resistance. So that would be 10 volts, right? So VI is 10 volts, yep. Times 1,000 over 1,500 plus 1,000. So that's my 1,500, that's my 1,000. Okay. I'm trying to figure out what they're trying to calculate here. Am I missing a page? Or is this study guide really that garbage? 7, 3, no, that's it. Wow. Okay, so here's what they're trying to do. Is they're trying to find the voltage across a 1 kilo ohm resistor, which is this guy right here. So VI, it doesn't explain what the hell VI is, right? And that's why this is absolute garbage. V source is the 10 volt, so that's why they have the 10 here. And we got 1000 over 1500. VI is the voltage across the resistance, Ri, R1, R2, etc., and other resistors in the circuit. V source is the voltage. I have to tell you that this really pisses me off how they structured this, because they do tell you VI is the voltage across the resistance. That's across the entire thing. This study guide is absolute crap. Absolute crap. I should have just did this with the formulas. Absolute garbage. Okay. So here's the thing. It's trying to find the voltage drop across the 1 kilo ohm resistor. So I take it, you take the resistor that you're trying to find, and then you do that over the 1500 plus 1000 equals 4 volts. So in the same way, we could find the voltage across the 1.5, so that would be 1500 over 1500 plus 1000. $10 volt times 1500 over 1000. Let's do the math. 10 volts times 1500 divided by 1500 plus 1000. And close parentheses. And I am pretty sure that that is not correct. Definitely not correct. Of course, it would help if I'm not using my phone calculator. $10 volts times, and in parentheses, 500. Divided by 500 plus 1. Yeah, it's going to give me the same garbage. So they're basically creating a voltage divider, but it poorly, in my opinion, expresses how it does what it does. Here, let's use their example. We do 10 volts times, I know it's the calculator that's going to mess this up, 1000 divided by 1500 plus 1000. Close that off. Yeah. Fuck this stuff. Sorry, guys. Well, I mean, yeah, you could do 2500 on the bottom. But the key is to figure out the parentheses and stuff. Well, I mean, it's not like we're going to use this as the calculator on the test anyway. Let's see. Does it actually change if we use the scientific calculator? So we got 10 volts times 1500 divided by 1500. See, they're using simple numbers, but while you can add it in your head, I mean, trust me, when you start adding like multiples of multiples, you got to figure out the process, and that's what I'm really kind of working on now, is to find the process. Okay, so that says 6 volts. So basically what I did is I basically did a parenthesis, and then I did another sub parenthesis down here, and then I closed it like that, and it gives me 6 volts. You know, this is going to sound really stupid, guys, but since I had 10 volt as my origin, and I already knew that it dropped 4 volts across the 1000, that means that it had to drop the rest off the other one, right? I could have just used deductive reasoning. However, the whole purpose that I'm going to this through length is because if I do have a calculator and I am sitting down to cover this kind of material, I need to figure out where I'm going to place the parentheses and stuff so the calculator is going to give me a correct answer, because I'm going to absolutely lose my gourd if I'm sitting there at a test and I'm fighting my test equipment. So that's why I'm sitting here and I'm drawing this out and I'm running it multiple different ways. Sorry guys, but that is just for me to figure it out, you know, so that when I take my test in 2 days time, I know what I'm doing. Find the current through the 50 ohm resistor. Lovely. It says current division is the splitting of currents among branches of a circuit. With resistance in parallel, the circuit through any branch can calculate by an equation. Jeez. I certainly hope they give these formulas for the test. Certainly hope it, because other words, there is no effing way. No way. Current division. Where I over I is the current through the resistance, Ri, R1, R2, etc., and other resistors in the circuit, and I source is the current of the main branch. Okay, find the current through the 50 ohm resistor. Well, so they're not giving me the voltage, but we can figure that out. So we know that no matter what, across all of these, they're dropping, and they've got 600 milliamps of current. So what they're doing is the I source, hold on. Yeah, it follows through on the next page. Here, I'll tell you what, let's go ahead, let's get out the sheet of paper. Jeez, you can tell my kids have had my my notepads. All right, let's do this. So I source, so the current at the source, because right here's the battery, and they're showing the leg off the battery, so that's the total current of the entire circuit. So that's 600 milliamp equals, here we go, I over Ri. So which one are they trying to find? So that's 50 ohm. So that's 1 over 50, which is over 1 R1, 1 R2. Okay. So that's 80 ohms plus 1 over R2, which is 50 ohms, plus 1 over 200 ohms. And then, so what I'm going to do is I'm going to do a parentheses down here, and then I'm going to close it with a parenthesis. You understand what I'm doing? So the calculator should be able to figure that out. Oh, shit. Sorry, one other thing. This is not equal. This is multiplied. That's how you know I'm tired, guys. That's okay. We got 600 So that's milliamps. So of course we're going to give them a response back in milliamps, so I'm not going to convert that, times, and let's do our first parenthesis, which is going to be 1 over, let's see, my own formula, 1 over 50, parenthesis, divide by, do it, we do another parenthesis there, divide by, do another parenthesis. I love computer programming, so I hope that my calculator can handle these amount of parentheses. 1 divided by 80 plus 1 divided by 50 plus 1 divided by 200, parenthesis, is the first one, parenthesis, second one, should be good. So I have a result of 320. So that's 320 milliamps across the 50. Okay. So you got that? Let's see if I'm right or wrong. All right. Yes. That's why we're doing this together, folks, because once I figure out the parentheses and where to put them, no problem. We got this. So right here, you can see we got 600 milliamps, and they did the single parenthesis 1 over 50 plus 1 over 80 plus 1 over 50 plus 1 over 200, 320 milliamps. So because it has the least resistance, it's going to get a majority of the 600 milliamps worth of current. Yes. Okay. I feel good about that. Okay. No problem. I just had to remember to do the multiple parentheses, and you guys seen the formula on my calculator. It was actually long and drawn out. So let's go ahead and let's change this up a little bit. Let's figure out the current across the 200 ohm resistor, since the 200 ohm resistor is the one that's going to get the least amount of current because it has the most amount of resistance. Let's figure out how much current it's dropping. So let's go ahead and let's clear it. We got the 600 milliamps, and we're going to do times, first parenthesis is 1 over 200, close that parenthesis, and divide by, and we're going to do another parenthesis. I know I'm changing the parentheses yet again, but that's because I'm testing how many parentheses I can put in there and get the correct answer, because I love sectioning things off for up here. So we got 1 over 200, so that's what I'm doing right here is this formula. Oh, let's cross that out. So 1 over 200 and divide by, and then I put my second parenthesis, so it's 1 over 80 plus 1 over 50 plus 1 over 200, and let's close that parenthesis and the second one, equals. So we have 80. So this one here gets 80 milliamps. And I mean, through deductive reasoning, we can figure out the third one. All right. So we got 600 milliamps. So let's do, here, let's try it. 6. Sorry guys, can you see that? 600 minus 80 equals minus 320. So that tells us that we have about 200 milliamps of current across the 80 ohm resistor. So now what we're going to do is we're going to prove it. I love proving it. So times our first parenthesis 1 over 80. 80 ohms, sorry. Okay, divide by. Then we're going to do another parenthesis right here. 1 over 80 plus 1 over 50 plus 1 over 200, parenthesis, and big parenthesis to close it off. Are we correct? 600 times first parenthesis, second parenthesis, 1 over 200. Oh no, we're doing 1 over 80. Oop. Close it, divide by, second parenthesis, and we're doing 1 over 80 plus 1 over 50 plus 1 over 200, close it, equals 200. There we go. The maths. Okay, got a grasp of that. All right. Do you guys have any questions on that? Oh, holy cow. Hold on. I'll get to your questions in just a moment. So, Romeo is saying if you find yourself in a situation where you're nervous or whatever and your brain gets a little scrambled, you can use your calculator to find each piece of the equation. Absolutely. And that, believe it or not, that's just how I work. And you guys can see it here, how I like piecing it out and solving all of it to figure it out, because that way there I can check my work and I know I got the correct answer. If you only solve part of it and maybe you're missing some other values, you're not going to know for sure. You're kind of taking a guess. So if you're missing some of the values, you might as well solve for each of the resistors so that you can check your own work. All right. And then do the totals after, more manual, but after you get confused with the parentheses. So I don't get confused with parentheses because my brain is just programmed that way. I've done computer programming since 1993. And, you know, using parentheses, especially, I don't know if you guys do Excel very much. I love Excel. But in Excel, you keep track of your opening and closing remarks. And in doing so, you know, you segregate out sections of data and you process it in chunks. And the chunk, each chunk, you can do in parentheses, even though like the masterminds behind it, they kind of group a bunch of things together under one opening closing mark, you know, like a paragraph. I do like subsets, and in doing so, it's also much easier for me to troubleshoot later on, unless it's like a batch argument or something, and then I'll do it as a group. But anyway, who's taking the CBET, the next testing cycle? Well, I'm taking it Wednesday. So I got just today and tomorrow to study. Okay. All right. So there we go. All right. Kirchhoff's current law. This should be interesting. KCL states that the amount of current flowing into a node must equal the amount of current flowing out of it. Okay. I in must equal I out. Summing all incoming currents and setting it equal to the sum of all outgoing current will allow the calculation of any single flow of the node. This is known as nodal analysis. Jesus, I hope this isn't on the test, because when have we ever had to do this garbage whatsoever in the field? Anyway. You just have to attention to detail and know that what they're saying is the current coming in must equal the current going out. And so you see right here, I've got an unknown value. I've got 6 amps and I have multiple outgoing. So incoming, I have 3 amp, 6 amp, and an unknown. So what we want to do is take all the outgoing currents and then we're going to do some quick math. All right, so let's go ahead and write it down. So incoming, I have 3 amp. I have 6 amp, and I have unknown, and outgoing, I have 1 amp. See if you guys can see it. I have 3 amp, and let's see, 2 amp. So what we do is we add them up. So right here we got 6 amp, out, We have 3, 6, and unknown coming in. I am doing that correctly, and am I not? Wait. Hold on. Because the math is not jiving there. So I'm doing it correctly here. 3 plus 6 plus unknown equals 3 plus 2 plus 1. So what is it? Is it 0.5 or 0.25? Because I have too much here. So 3 plus 6 plus question mark equals 6. Okay, so what doesn't make sense here is they should have left that arrow off, because that's kind of stupid. All right, and the reason it's stupid is because they should have just said I2, and which way is it going? Is it coming or going? Because they say that it's incoming current, but it's a negative number. There's not a negative current, guys. So what they're saying down here is I2 must equal negative 3A. There is no such thing as negative 3A. This is the kind of garbage that I absolutely hate about studying for these kind of things, is that type of crap right there. So there's no such thing as negative 3 amps, all right? So it's 3 amps, but it's outgoing, okay? So they shouldn't have drawn that arrow. That's misleading. So that's why I was saying the math isn't mathing, because it would have to be a fraction in order to draw these numbers down. So we're at negative 3. So in other words, what we're saying is we got 3 amps out. So that would actually come over here. So we got 6. Yeah, so technically that's 3 amps on the out, not 3 amps on the in. That's stupid. I'm just telling you right now, that is stupid. All right. This right here, I'm telling you right now, that's stupid. They should have left that arrow off, and then it should have had a question mark so that you could, if you said negative 3 amps, that means that it's leaving, and it's not coming. Or they should have you drawn an arrow saying, is it coming or going? Anyway. Kirchhoff's voltage law, KVL. KVL states that the sum of voltage drops across all devices in a closed loop of the circuit will always be 0. This is a good one, because I have had to do this in the field. Okay. Using this information, an equation can be formulated that will allow the calculation of the voltage across any single element in the loop, assuming all the other voltages are known. This is known as mesh analysis. For example, in a circuit, all the voltage are known except for VR4. So VR4, that's the voltage drop across resistor 4. So here's resistor 4. So this resistor up here is dropping 3 volts, 2 volts, 4 volts. I have 10 right here, okay? So what we're going to do, all right. God, I hate the study guide, because they don't really explain. They should have the formula up here and then show you what the formula equates to down here relative, like VR1, VR2, VR3, VR4 question mark equals. That's not how they did it. It says the equation for the loop is 0, because all sum has to be 0, equals negative 10, which is your source voltage, plus 3 plus 2 plus 4 plus whatever. So 3, 2, 4, it has to equal 0. We got negative 10. So 3, 4, 5, 6, 7, 8, 9. So we have 9 across these 3, and then that means that this one here has to be 1. So this right here plus negative 10. All right. So It's got to equal 0. This one does make sense. And I also draw my symbols. So if you see me drawing like ohms and volts and stuff, that's because it's too easy to get confused. Like over here, you see that I draw my ohms. Because when you start talking like milliamps and stuff, if you just start writing down numbers, you're gonna absolutely get lost on your percentage or your unit of measure. So, all right. Romeo says that he took basic electronics a long time ago. So did I. So did I. It was like 21 years ago that I took it. Okay, so VR4 must equal 1. Kirchhoff's voltage law. So that's for calculating voltage drops in a series in a closed loop. Yeah, some of these, it's just going to be worth it taking the hit and saying, yeah, if that question pops up on the test, I'd rather just miss that one and make sure I get other ones further down the test correctly. All right, inductors and capacitors. Now, I don't think that we should have to go into a huge amount of theory on inductors and capacitors, because how often do you have to mess with that? Honestly, you mess with resistors more than inductors and capacitors. All right, inductors. They're electrical devices that resist changes in electrical current by storing energy in magnetic fields and releasing it as necessary. They're usually made of a coil of wire wrapped around a core of air, iron, or ferrite. Inductance is measured in henries, or more commonly, millihenries. That's mH. And proportional to the number of turns in the coil. So, more turns around a coil or a transformer or whatever, and you have more inductance because there's more magnetic field that's being captured. Likewise, capacitors are electrical devices that resist changes in voltage by storing energy in electric fields and releasing it as necessary. They're usually made of at least 2 electrical conductors separated by an insulator, and that insulator could be air. It could be. They're usually made of at least 2 electrical conductors separated by an insulator or dielectric. Capacitance is measured in farads, or more commonly microfarads, and is proportional to the surface area of the conductors and inversely proportional to the separation between the plates. What does that mean? Who knows? As the numbers go up, they hold more charge. The end. Okay. Impedance. Alternating current in an is an electrical current in which flow of electrical charge periodically reverses direction. The nature of inductors and capacitors is to oppose changes in current and voltage, respectively. The opposition is referred to as impedance and is similar to resistance, also having a unit of ohms. However, unlike resistance, impedance is a complex value, meaning it may have an imaginary component as well as real component. For ideal capacitors and inductors, impedance is purely imaginary, and for ideal resistors, impedance is purely real. Now, have you guys ever measured a speaker, and it's a coil, right? And if you measure it while it's static, you can probably get your 2 ohms, 4 ohms, 8 ohms, whatever. However, if you move the speaker just a little bit, kind of like a motor, you can measure a coil on a motor, but if you move the motor, that value is going to change amazingly because you are inducing an electromagnetic field, and in doing so, you're messing everything up. So impedance and inductance. Complex impedance. Oh, Jesus. I really don't want to get into this. It's only when combining the effects of inductors and capacitors that the full expression for impedance Z is necessary. Z equals R times X times I, R plus X times I, where I equals the square root of -1, X is the quantity of known reactants. The reactance of a capacitor is XC, which equals 1 over W. God, jeez. I'm not getting into that, guys. Sorry. I think that's absolute trash. Hopefully it's not on this test. Absolute trash. My opinion, trash. Next, let's get down to passive and active devices. Passive electronic devices or components exist in two categories: those that consume and those that do not produce energy, and those that cannot amplify signals. Passive devices include resistors, capacitors, inductors, and memristors. Memristors. These components do not require energy to function, although they affect the circuit they are part of, and they may store energy or increase voltage or current. They can be parasitic, though, and they can take small amounts of energy. Active components are those that require energy to function and have gain, increased power within the system. Transducers. Transducers convert one form of energy into another. When referring to transducers that convert electrical energy to another form, vice versa, they're often termed electrical transducers. We have all sorts of these in medical equipment. Types of energy that can be converted with transducers include mechanical, electric, magnetic, chemical, acoustic, electromagnetic, light and radiation, and thermal. Transducers that convert other forms of energy and output as electrical energy are referred to as sensors, whereas those that take electrical signal and output another form of energy are called actuators. So one of the things that you have to understand is that all of these are analog. So analog versus digital. Digital is ones and zeros, and they take a computer to interpret. These are all analog. You can have an analog circuit, like right behind me. I have technically a temperature transducer that is completely analog. It has a sphere that is heated up, and that creates pressure, which goes down and actuates a microswitch. That is a temperature transducer. It's analog. Likewise, the voltage response that you're going to get if it's an electrical transducer is also analog. So you need an analog to digital converter in order for the computer to understand what is this magical voltage or resistance or whatever it is. Now, another version of a transducer is a thermocouple, a temperature transducer, which I thought I had one here. It's an analog signal, and it has to go back to an analog digital converter to where it analyzes it and it measures it across a known value, and that's how you get your magical, readout on your multimeter and stuff. So, transducers. All right, power conditioning. Power conditioning is the modification of electrical signals to reduce signal noise and ensure quality performance in electronic devices. This is accomplished through a combination of circuit components including amplifiers to raise voltage of a signal, the gain, voltage regulators, voltage dividers, current limiters, electronic filters, which remove unwanted parts of a signal, oscillators, which create a sine or square wave from a signal, and wave shapers. So there are lots of different types of oscillators. A lot of oscillators are still being used to control the clocking for digital circuitry, which I don't know if they're going to talk about here. We're going to find that out. Oscillators also do other pretty amazing things when combined with resistors and capacitors. An oscillator can also do some pretty cool stuff. So I don't know if they're going to get into that, so I'm not going to get into it. True, reactive, and apparent power. True power is known as real power measured in watts and is equal to voltage times current. P equals V times I. See, it comes back. Reactive power, Q, is measured in volt amperes reactive, VAR, and is a measure of power in which voltage is out of phase with current. Voltage is always out of phase with current. The watt, volt ampere, and volt ampere reactive are dimensionally equivocal quantities, such as 1 watt equals 1 VA equals 1 VAR. Now, where have you heard 1 VA? 1 VA is, the VA is typically how things like UPS systems are measured. So when they say 1 VA, if you see here, it says 1 watt equals 1 VA equals 1 VAR. So a 1000 VA UPS system can handle 1000 watts for a period of time. The combination of true and reactive power gives apparent power, S in volt ampere. You know something, I'm not even going to get into that. Just, I think that that's all crap too. That's absolute garbage. Types of electrical filter circuits, something you should know. Go figure. Electrical filters are used to keep or exclude certain parts of an electrical signal. Filters can be passive, using only passive components, or active, using active components, often including operational amps or op amps. 4 major types of filters include high pass, low pass, band pass, and band stop filters. High pass filters suppress signals below a certain frequency, whereas low pass filters suppress signals with a higher frequency. Well, if we're talking audio, the human ear can generally hear between 20 hertz and 20 kilohertz. That's 20,000 hertz. That's 20,000 times a second. So that's only 20 times a second to 20,000 times a second. That's most humans, their capacity for hearing when they're prime. So what they're talking about is a low pass filter takes just the low, and there's going to be a cutoff frequency. That cutoff frequency is going to be like 100 hertz, 120 hertz, 150 hertz. So basically everything from 20 hertz to 150 hertz, that goes to your amplifier and out to your magical speakers. That's why you have subwoofers. Now a high pass, so if you have the little tweeters, which are the little tiny speakers, you want to create a high pass, so that they only get high frequencies, because they require micro oscillations of the diaphragm versus low frequencies, which are large, slow moving sine waves. Those ones will damage things like tweeters. All right. So speakers specifically are designed according to a certain frequency, and you need a active or passive filter circuit in order to make sure that only the signal that is designed for that speaker gets that speaker. That's just for audio. Now this is for all sorts of electronics. We have all sorts of things. Like let's take for instance cameras. Almost every single camera out there has a 60 hertz filter, okay? And that's because here in the United States our frequency, our line frequency is 60 hertz. So that means that LEDs and stuff tend to turn on and off at 60 hertz, which according to your shutter speed, etc., it could create some problems. So what they'll do is any type of electrical cables that come and go around certain sources, they will have filter circuits to try and notch out that 60 hertz or whatever. So that way there, the 60 hertz doesn't end up on things like your ECG. So your ECG naturally wants to vibrate at 60 hertz because all the lights around you are 60 hertz. They're flashing on and off. So normally your ECG would be flopping at 60 hertz too, because it's basically just an amplifier. But because it has the 60 hertz filter, it's going to notch out 60 hertz so that all the other signals that show up can be read nice and clean. So you are going to see filter circuits in real medical equipment. Operational amplifiers. Op amps, the workhorses of electronics. Op amps are analog circuit components that amplify the difference between two voltage inputs. Formerly known as differential amplifiers, that's what I remember them being called. Op amps have two inputs, inverting and non-inverting, one output, and positive and negative power supplies, which are usually implied in circuit diagrams. Now, let's see. I should pull those up so that you guys can see them. We'll see. They're probably not going to get into it too much. Internally, op amps contain many transistors and resistors. There are several key characteristics of op amps. They have a high gain and can amplify the input voltage as much as the power supply input. An ideal op amp would have infinite gain and no current at the inputs of the amplifier. So what they're saying is that it can output as much as you want, but at the inputs, there's no current at the gain. So in other words, if I'm sitting here tugging on this paper, you know, it's creating a wave on the output. So if I input a slight wave, its gain, its output is much greater on the other side without being parasitic to the input. Parasitic means that it's pulling current. So all semiconductors do pull current in order to function, unfortunately. So that's why they're saying the ideal semiconductor, it wouldn't have any current at the inputs. In other words, you flash, you know, 10 volts at, you know, whatever, and it's going to be 10 volts, 0 amps at that input. It's not going to be parasitic. That's what they're saying. Power distribution in the United States. I did a whole video on this, guys. A whole video. I don't have it here. However, I did a video discussing the power grid in the United States. Power distribution in the United States includes AC current, which a voltage that is amplified to a high transmission voltage via transformers from power plants or generators is sequentially stepped down at receiving stations, substations, and distribution stations prior to reaching consumer at 240 volts. Common for 60 hertz frequencies used in the United States. So here's the thing. When you have a transformer, the input frequency is the exact same as the output frequency. The voltage will go up and down just like the current will go up and down, but the input frequency is going to be the same on the input as the output. So let's say I have a transformer that's got one turn on one side, and I have a sine wave at 1 volt at 1 hertz coming into the input. Here, let's draw it out. Let's draw it out. Because transformers are one of the things that I believe are probably some of the most misunderstood things, and they're absolutely essential in real biomed work. Okay, so let's say here's this. Here's my outputs. So here's my primaries. Here's my secondaries. So let's say we have, and we're going to do 1 volt. And let's say we got a 1 to 10 ratio. So, and that means for every 1 turn on the input, there's 10 turns on the output. Okay? So that would mean that we have 1 hertz at 10 volts on the output. You understand? So the transformer is 1 to 10. So 1 coil, 1 turn here, we got 10 turns over here. If we got 2 over here, we got 20 over here. That's your 1 to 10 ratio. The frequency is going to be the same. Now, why is that relevant? At your power station, they're creating electricity at 60 hertz. And you actually adjust the generator or the steam plant plus or minus the output to make sure that you keep the frequency the same. So the voltage might sag or go up or down, but the frequency is most important to keep that as close to where it needs to be as possible. So in a power station, you could have 60 hertz, and we have 60 hertz. Okay, but imagine this. It goes from, let's say, 6,000 or 10,000 volts. And then it goes to a transformer. Okay. Something like that. Anyway, oh, sorry guys. So let's say 10,000 volts here. It's going to exit out at 100,000 volts. Now when you see some of those high voltage power lines, so if you look at that, if we get 10,000 volts in, that's what, the 1 to 10 ratio that we talked about up here, right? But it's still at 60 hertz. And then this transmit over the power line to your house, where in my video I talked about the Edison or the split phase system, and you're going to have a transformer there. So you got this guy here, you got your transformer, and I understand that I'm not doing this justice. I'm okay with that. So we still have 60 hertz. It's down to 240 volts in the United States. So the constant is the frequency. The frequency does not change in a transformer. Okay. Now you can change frequency with other things, like we have variable frequency drives and stuff like that. But this is the primary reason the frequency is the same, which is why motors and clocks and stuff like that run at a certain speed. AC motors run at a certain speed. It's based on its frequency, and clocks often use the line frequency to help them compute their cycles because of their oscillator. Modern day clocks don't, but the older ones do. So, guys, that goes to tell you, power distribution. Now these numbers here are hypothetical. The 100,000 volt and the 10,000 volt. Watch my video on it. I did it probably 3 or 4 months ago, 5 months ago. Just type in, go into Better Biomed and then type in like power and you'll see it. So anyway, that's transformers. Okay. Inductors, capacitors. Let's get rid of that guy. Guys, we're almost done. Last page, folks. Last page. Now, I love transformers. Decepticons. I love them. Transformers are the basis for every single thing that we have in modern day electronics. Transformers are from audio to even cute little guys like this microphone here. Would not be possible without transformers. And specifically, we got these transformers to convert electricity that steps up and steps down, and it also makes stable electricity, but it also creates safer power because we have, where are they? All right, here's one right here. What? You guys have seen this before. Now, how is it that I'm talking about transformers? And here, I have one of these guys. Come on, you guys have seen these before. You guys have these all over your house. Hell, even your cell phone chargers, your little USB chargers. Guess what's inside them? Transformers. Look at this. I have a switch mode power supply here. Look at this. I got dual transformers running in parallel with secondary transformers. Whoa! With a, we have chokes and stuff. And chokes are also transformers, per se. So, I mean, think about it. The other purpose that transformers do is they isolate power, and they have made electronics exponentially safer than what they used to be. Now, things like that M4 Chattanooga that's back behind me here, I talked earlier about how if it has a short, it's a huge liability, because let's say there's any compromise whatsoever to the ground pin. What are the odds of that happening? If that ground pin is compromised, it's no longer getting rid of that leakage. And if you go up and you touch it, you can and will get shocked because it's run straight off AC power. Switch mode power supplies, external and internal, they isolate the power. And not only do they drop it over to DC, which is generally safer, low voltage DC is safer for us to operate with and it's safer for patients, but it also isolates you and the patient from mains, AC mains. This and this are two different things. This is much safer than this. If you get this wire here, I can strip this while it's plugged in, while it's live. I can probably strip it with my mouth, no problem. I might feel a little tingle. You're not going to do that with this side, okay? You're not going to do that. Exponentially safer to have switch mode power supplies. You wouldn't have switch mode power supplies without transformers. There you go. Characteristics of transformers. Transformers are necessary components for devices that need to deliver high voltage, such as defibrillators. Transformers, well, wait a minute, that's their only line? They're necessary for components. They're necessary components for devices that need to deliver high voltage. What about low voltage? You're not going to get low voltage without it either. What the? Come on. All right. Transformers are devices made up of two or more coils of wire that are used. They use induction to create a transfer of energy between circuits. A step-up transformer's input, the primary voltage, is lower than its output. Now, the diagrams that I drew for you guys are a step-up. When I said a 1 to 10 ratio, that is a step-up of 1 to 10. And a step-down transformer's input is higher than its output voltage. Now, we had these all the time over in Europe, specifically. I can remember them. A lot of Americans would take their 120 volt electronics over to Germany in the military, and they would use those stupid adapters and they'd plug it straight into the wall, and it would catch fire. You need a step-down transformer because Europe in general runs on it's 240 volts. American is 120, so there is a 2-to-1 step-down transformer. And that basically creates a, remember I said the frequency stays the same, so it's a 120 volt, 50 hertz. You can't change the hertz, you know, it is what it is, unless you get a frequency converter, which, Jesus, you're talking a whole nother lecture there. So, step-down transformer, we used them all the time in Europe. This allows for electricity to be generated safely at a lower voltage, example 12 kilovolts, pass through a step-up transformer for transport through power lines at high voltage, 400 kilovolts, and pass through a step-down transformer for distribution at your house, an example, the 240 volt residential. Now, they didn't talk about the frequency on any of those, and they really should have. A lot of people think that the frequency also doubles, etc. It doesn't. It says ratio of turns where V and N, yada yada. Not going into it. Performance characteristics of batteries. Are they really only giving me... Oh, come on, guys. So one, they're not talking about power supplies. I hope they're talking about power supplies on the CBET test. Because if you don't know power supplies, you're not a certified biomed. I don't give a shit who you are. If you don't know power supplies, you are not a certified biomed. We deal with power supplies more than anything. It's the Achilles heel of almost any electronic. And I don't even see them talking about it here. Performance characteristics of batteries. Several characteristics of batteries determine their functionality. The voltage per cell, which for common AA batteries is simply their voltage as their single electrical cell. The chemical composition of the battery's anode, cathode, and electrolyte. So we have alkaline batteries, we have nickel cadmium, we have lithium polymer. All these describe the chemistry and or the construction of the battery. The energy by weight of the battery, known as its energy density, which lithium right now is king. The internal resistance of the battery, we did a whole video on that about measuring resistance of a battery. Mind you, with batteries, the lowest resistance is always going to get the most amount of current. So if you are charging a battery and you have one battery that's much lower current than the rest, then that battery might catch on fire because it's going to get all the current and it's going to get saturated until it's completely charged before any of the other batteries that are in a series or parallel configuration. Electricity always goes to the path of least resistance, right? So, the internal resistance of the battery, which affects the use and duration of a charged battery. The shelf life, which is a measure of the battery's ability to maintain a charge while disconnected and unused. And the battery's voltage discharge curve, which that's an interesting one. Maybe I should do a video on that. There is a very direct discharge curve, like with, let's say, lithium polymer batteries, like in my phone. It's going to be like the curve is going to go a long way out, and then it's going to start dropping off. And then at a certain point, it's going to drop off quick. And when it drops off quick, that's when you get into cell damage, permanent damages. So we don't have that problem with other types of batteries like nickel cadmium and the nickel metal hydride. Those type of battery chemistries are more durable. However, the energy density is much lower than lithium. Lithium's king. Depending on the device's voltage requirements and for rechargeable batteries, the number of charge cycles. Important. That's why the whole thing behind like electrical cars is nobody is talking about the amount of charge cycles that you can do and its expected life. And one of the things they didn't talk about is the characteristics of batteries is its ability to operate in certain climates. If it's encapsulated, it's going to develop its own climate. In other words, if you seal batteries in a watertight container and there's not very much air to help cool it off, its life is going to be less. However, a battery that's exposed is going to have a much longer life. So even though it might have 2,000 charge cycles, seems like a lot, it's really not. And there's also expected life. So let's say car batteries. Two different types. For regular car batteries, lead acids, you got 12 volt batteries usually, and I change mine out every 3 years. And I do that intentionally because after 3 years, lead acid batteries, especially depending on the climate that you operate in the car in, they become rather unpredictable. Yes, you can test them with a tester. However, I don't like getting stranded. I don't know about you guys. So every 3 years, what I do is I change out my battery and I bring my old battery here. I have a junk battery that I use as my core. And I keep one battery always charged here in my shop. And I do that so I can A, either jump another car if I need to. B, I have a backup. Or C, I have inverters. So if I run out of electricity, I can hook up these car batteries and I can use them to generate AC electricity. Not very efficient, but it does work. All right. So performance characteristics of batteries, you got the chemistry, you've got their shelf life. I was talking about electric cars. Nobody wants to talk about the fact that electric cars also have a life expectancy and charge expectancy on the batteries. You have a certain number of cycles. And those batteries are crazy freaking expensive. You know, you can get some of those batteries for like $7,000 or $8,000 if you're lucky. As some people have found out, some of those batteries can be $20,000, $25,000 depending on the model of the car. Maybe even more, especially if you get a luxury car and it's a smaller production cycle. The thing is, you have a certain number of cycles that you can run on that battery. Climate does affect them. So if you're in high heat areas or if you're in areas where it's extremely cold, the life expectancy on those batteries is much, much less. So if you are in like Colorado or New York or my home state, Michigan, you got an electric car, good luck, buddy. Good luck. You've got 3 to 4 years on that battery before you start experiencing error codes and other problems. And good luck with the cost on changing out that battery. So, performance characteristics of batteries, there you go. Uninterruptible power supplies, UPS systems. It's used as a backup measure to ensure critical medical devices remain powered in the event of a power outage. This protects against brief outages and periods of main power outage and the start of the hospital standby power. UPSs generally consist of an electromagnetic filter, surge suppression, battery charger, voltage regulator, which function during normal operation, and a battery that runs when AC power is not provided. Now, they do some other fascinating things. There are different types of UPS systems. There's some that are always generating a sine wave. There's some that are switched. I did a whole video on UPS systems. Go check it out. And it's going to go into some of the details of the UPS. Now, there are some systems that are always running off the battery. So in other words, when you connect it to the wall, it's always charging that battery. The device is always running off the battery. But remember this one single thing. We have a sine wave, right? And in the United States, let's go from this point right here and this point right here. So between these 2 points, that is one wavelength. And as I already said, in the United States, it's 60 hertz, okay? So since it's 60 hertz, what that gives you is an eternity. It seems like it's fast, right? It gives you an eternity for a UPS system to activate, all right? So it doesn't have to activate within this, because remember, there's something called hysteresis. And hysteresis is the amount of electrical charge that stays in the circuit. And that gives you a little bit of buffer. Because remember, if we were to take this like this, so let's say that this here is 0 volts AC. So at the 0 volt line, there's technically no potential whatsoever, right? So it goes positive, the current's moving this way, and then it goes negative, the current's moving that way. So, and it's doing that back and forth, 60 times a second, right? However, when a UPS system senses a disconnect of power, there's a little bit of hysteresis in there, which is a buffer of time when the device that's under power is accepting current. And certain things like this right here increase that factor because it's got capacitors, right? And those capacitors are gas tanks for electrons. So what you can do is your UPS system, it can keep putting out, it switches over to run off the battery, and it does it within this period of time because there is a buffer between the next cycle. So there's no voltage here in the middle, so it's voltage, 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 voltage. There's always this period where there's none. And if there was no hysteresis whatsoever, which is the ability to store some sort of charge, then your device would be shutting on and turning off, right? All computers, almost every device out there has some sort of capacitors or something that give it a level of hysteresis. It's a buffer of time before it runs out of juice, right? So you can take an electrical cord. Matter of fact, I just use this as an example. Hold on, where is it? Where is it? Where is it? This guy. You guys ever have one of these guys right here? You have one of these guys, you plug it in, maybe it's got a little green LED, and you disconnect it from the wall, and that green LED stays on for a little period of time because those capacitors that are inside it, they're discharging. That is a type of hysteresis. It's a capacity of electrons before there's none, and that buffer of time gives the UPS system the ability to switch over and start generating a sine wave on its own out of DC power. So it's creating AC out of DC. It does that because we are only cycling at 60 hertz. It would be much more difficult if we had electricity that was cycling at, say, 1 kilohertz. If we were at 1 kilohertz 1,000 times, it would be like that instead of this large, slow-moving wave. There would be much less hysteresis down here because when you cut the power off here, you're going to have a lot less on this guy than this guy, if that makes sense. So UPS systems, all they do is they sense when the current is no longer changing directions, because remember it's 60 times a second. When it's not changing that direction, it says, hey, switch. And it switches over because it loses that difference of potential. And when it starts switching over, you can hear those little SCRs, the bzzz. What they're doing is they're switching on and off, and it's creating a waveform. So it's sending some current this direction and some of it that direction, you know? So in other words, it's like taking a RC car and switching the battery like this, back and forth, back and forth. That's technically what UPS systems do. So guys, that is electronics according to these guys, and I think they missed a hell of a lot of stuff. Matter of fact, I'm a little confused because I think they missed out on a lot of stuff. They truncated AC power down to like a paragraph or two. I don't know, guys. Anyway, tomorrow morning, guess what I'm doing tomorrow? All day. I'm not necessarily going to be doing live streams. I'm not really sure. I think at least in the morning I'm going to, until my voice starts running out. We're going to cover understanding test equipment, and we're going to cover a lot more of this tomorrow, okay? So that is rudimentary electronics, but tomorrow we are going to go into some other stuff, okay? All right, guys, I know I've been rambling on. Thank you all for watching, and obviously I'm extremely tired, so I apologize if my rambles have gone on and on. However, tomorrow, I look forward to it. If you want to join me throughout your day. If not, these videos will be archived. You can look them up at any time. You can go into Better Biomed on YouTube. There are different things. There's shorts, there's videos, and then there's live. You click on live, and you can see all my previous live streams, which include these, and you can partake. You can even fast forward and rewind to the part that you like. And as always, you know, you have some comments, please feel free to leave them down below. I will read them as I get into it. So, thanks for watching, guys, and hope you guys have a fantastical night. Holy